Our entire digital world, from AI to the cloud, it all lives inside these massive city-sized factories. So today, we're going to break down exactly what it takes to build one of these billion-dollar data centers from the ground up. We hear about the cloud and AI all the time, right? But have you ever stopped to think about where this stuff physically exists? It's not in some abstract digital space. Nope. It lives inside very real, very large, and incredibly powerful buildings. And when I say powerful, I am not kidding. A single one of these, what they call hyperscale data centers, the kind you need for this AI revolution, can have a power capacity of 100 megawatts. It's just a staggering amount of power. To really put that in perspective, a single 100 megawatt facility uses as much electricity as about 75,000 homes. Think about that. One building using the power of a small city. This kind of scale changes everything.
So here's the crucial point, the thing we all need to understand. We have to stop thinking of the cloud as something soft and weightless. It's not a cloud, it's a factory. A massive industrial asset every bit as complex and capital-intensive as a semiconductor plant. And this realization is driving an unprecedented AI infrastructure boom. The explosion in AI has created this absolutely insatiable demand for these new industrial buildings. We're talking about data center capacity that's projected to triple by 2030. It's just wild. Which brings us to the first major hurdle, the global hunt for power. Because when you need to power a small city in a single building, well, you can't just build it anywhere. There's a new #1 rule in this game. This reveals a really fundamental shift in strategy. It used to be about finding cheap land near the big fiber optic cables, but not anymore. Now it's a power-first model. The single biggest hurdle is simply finding a location that can supply the colossal amount of electricity needed. You can see all the critical needs here, from water to fiber. But the real showstopper is that top one, grid capacity. Just securing a connection to the power grid can add more than 3 years to a project. It has become the ultimate bottleneck. So let's say you hit the jackpot and you find a site with enough power. That's when the clock starts on an incredibly long and expensive journey. We're talking about a 6-year, multi-billion-dollar build for a single facility. This timeline shows you just how complex it is. The first 2 years are spent just on planning, design, and getting permits before a single shovel even hits the ground. That's because you have to pre-order critical equipment like massive transformers and generators that have lead times of 12 to 18 months. And the cost? Well, the total investment for just one 100 megawatt facility can top $5.5 billion. And that includes not just the building, but all the servers and those very expensive AI chips that go inside it. Now, when you look at just the construction costs for the building, it's really revealing. About half the entire budget is spent on electrical systems, the switchgear, the backup generators, the uninterruptible power supplies. It all comes back to that one core mission, delivering constant, reliable power. All of that power infrastructure leads us to the next massive engineering challenge. Once you have all that electricity flowing, you have to deal with its primary byproduct, an incredible amount of heat. You have to keep the AI brain cool. The heat coming off of modern AI hardware is just off the charts. Just a few years ago, a server rack might generate 10 kilowatts of heat. Today, some are generating over 50. Traditional air conditioning just can't handle that. It's now basically obsolete for high-performance computing. So to measure how well they manage all this energy, the industry uses a metric called power usage effectiveness, or PUE. It's a pretty simple ratio. It measures how much total power the building draws versus how much power actually reaches the computers. The perfect score is 1.0.
A PUE of 1.3, which is the target for these modern facilities, means that for every 1.3 watts pulled from the grid, 1 full watt is powering the IT equipment. The other 0.3 watts run the cooling, the lighting, everything else. And that is a huge efficiency gain over older data centers. So how do they achieve that kind of efficiency? By moving away from air and embracing advanced liquid cooling. For the most powerful AI systems, this means piping coolant directly to the chip itself or even fully submerging servers in a special non-conductive fluid. This all brings us to the future of the cloud. This massive build-out of digital infrastructure is running headfirst into some very real-world physical and environmental limits. Take water. The evaporative cooling towers needed for a large data center can consume up to 5 million gallons of water every single day. That's about the same amount of water that a small town uses.
And as the power grid gets greener, the next big sustainability challenge is coming into focus: embodied carbon. These are the emissions that come from manufacturing the concrete and steel needed for construction. It's the hidden carbon footprint of the building itself.
In response, the industry is exploring some really innovative solutions. Things like building their own power plants right on site, using recycled materials, prefabricating components in factories, and even capturing waste heat to warm nearby communities. Which leaves us with a final, pretty thought-provoking question. We've built this entire economic and social model based on infinite digital growth, but it all relies on physical factories that consume finite resources: power, water, and materials. So how do we reconcile those two? What comes next?